First speaker of this afternoon is Michele Cicoli. He's talk about Cosmology and Moduli Stabilisation for Chiral global models.
Yeah, okay. Let me start by thanking the organizers very much for the possibility to give this talk, which is going to be based on a few papers which I wrote recently in collaborations with different combination of authors, and mainly it's going to be based on the first one with my old friend Valandro, where we try to combine moduli stabilization with D-brane chiral model building in a fully consistent Calabi-Yau described in terms of toric geometry. And we did this using D7 branes in the geometric regime. Then in this paper with Goodsell and Ringwald, we try to analyze the consequences of that moduli stabilization scenario for axion physics, finding that actually you have an axiverse, so a plethora of light axions in the effective field theory. But I'll be brief on this because Mark is giving a talk later on. And then today, this paper came out also with Krippendorf and Quevedo, where we tried to sort of extend the analysis in the first paper to include also not just D7 branes, the geometric regime, but also fractional D3 branes as singularities. Sorry, well, let me go back and announce that even here I'll be brief because Sven and Christophe will give 2 talks on the details. So as you all will know, there are 2 standing problems of Calabi-Yau compactifications. The first one is to stabilize the moduli. The other one is to derive GATT or MSSM-like constructions. And type 2 theories turn out to be very promising because of the presence of D-branes and O-planes. So, you know, these local objects on one side, they allow you to circumvent no-go theorems and turn on fluxes that allow you to fix most of the moduli. And D-branes provide an abelian gauge symmetries. And the other thing, you can have a brane-walled scenario. So if the volume is large, then you can decouple these 2 problems. So that moduli stabilization is a global issue, model building is a local issue. Then physics decouples, then you can study these 2 things separately. And so far people did this, and in type 2b, where the fluxes have a mild back reaction on the Calabi-Yau, just induce a conformal factor, there are viable mechanisms to fix the moduli and construct semi-realistic models. So it is time to try to combine the 2 things. People already tried to do that. And of course, as you might have expected, they found that the 2 things are not completely decoupled. It's not that you have a solution, one problem, solution to the other, you put them together and it works straightforwardly. For example, these authors pointed out that there are some problems, and these 3 are the main ones. I'm just now listing them, and then I'll be more clear later on about them. So the first one is that there is a tension between moduli stabilization by non-perturbative effects and chirality. The second, there is again a tension between stabilizing the Chiral moduli by non-perturbative effects and the cancellation of particular worldsheet anomalies, Fried-Witten anomalies. And also the D terms, sometimes they induce the shrinking of various divisors. And this is a problem, for example, if they induce the shrinking of the overall volume mode. Or even if you assume that you are in the geometric regime, but then the D terms force you a shrink into 0 size. We will try to solve them having control over the effective field theory, stabilizing the moduli inside the Chiral cone, because we have toric geometry that is telling you what the Chiral cone is, and also trying to get some interesting phenomenological scales. So the main result is that we focus on type 2b F-theory compactification with the 3D7 branes and the 307 planes, where we have this explicit description of the compact Calabi-Yau by means of toric geometry. And we perform several global consistency checks, like the 7 tadpole cancellation, the cancellation of torsion charges, and Fried-Witten anomaly cancellation. And the only thing that we didn't check is the D3 tadpole cancellation, because we didn't turn on the background fluxes explicitly. But at least we checked that the total D3 charge is negative and large, so that there is space to turn them on. Then we managed to fix the Chiral moduli within the Chiral cone in the regime of validity effective field theory in a way compatible with chirality, and having these D terms under control. Finding 2 possibilities. The first one, as I was saying, with the visible sector, D7 branes in the geometric regime. And here we build chiral toy models with SU5 or MSSM-like models. And toy models in the sense that we never got the right chiral spectrum or Yukawa couplings, but this was not the main point. We wanted just to have something which was chiral. And then in the paper which came out today, we consider fractional D3 branes for the construction of the visible sector at del pezzo singularities. We have many models, but then so in the paper we work out in detail the simplest one, which is just a DP0 3-unification model like SU3 cubed, that then radiatively you can break down to left-right symmetric model and then to the MSSM. You can have realization of these large volume scenarios axiverse for global consistent chiral models, these ones, and Mark will talk about this. And then recently, in another paper with Marana, Quevedo, and Barges, we pointed out that not just the visible sector can be at the singularity, but also a hidden sector with non-perturbative effects can be at the singularity. And this might give you a new way to get the CTR vacua via these E-1 instantons. And finally, we had other papers. Maybe we'll have some time in the end to talk about that, but which are about cosmology with Pedro and Tasinato, and also with Yvonne Zavala, who is here, showing that the Chiral moduli are promising inflaton candidates. And for example, you can get inflation using poly-instantons that have been worked out by Blumenhagen and collaborators. But you can also have a multi-field inflationary dynamics that gives rise to detectable local non-Gaussianities detectable again by Planck. And also that the Chiral moduli, we show that they can not just explain the early universe acceleration, but also the present-day acceleration getting quintessence. So in type 2b, the closed-string moduli, you have the axodilaton and complex structure moduli, and the Chiral moduli, as usual, parameterizing the volume of divisors. And then you have an axionic part with the reduction of Ramond-Ramond forms. In general, you turn on these background fluxes that generate a 3-level superpotential that depends just on S and U. So S is the dilaton, U are the complex structure moduli. And you fix them just imposing F terms equal to 0. You have the no-scale structure, and the T moduli are flat at 3 level. So then you need to consider any kind of perturbative versus non-perturbative correction to fix them. And there you can consider just the 3-level superpotential as a constant, and the 3-level Chiral potential is minus 2 log of the volume, where the volume depends on this, on the divisors of the volume, on the volume of the divisor, so on the Chiral moduli T. And so in our paper, we consider all the possible sources for Chiral moduli stabilization, like D terms that you generate once you turn on fluxes. You generate moduli-dependent Fi terms. And you can parameterize the volume dependence of each contribution, and these are the leading ones, because they go like 1 over the volume squared. And you're always in a regime where the volume is large, so that you can trust your effective field theory. Then also the 3-level F would go like 1 over volume squared, but this is 0 due to the no-scale structure. And then you can have perturbative corrections like alpha prime or G strings, corrections of Chiral potential, that go like 1 over volume cubed or smaller. And the same behavior is true for non-perturbative corrections to the superpotential, like E3 instantons of Gaussian condensation. So generally what we did is that the leading order, you just have VD, and you fix some of the moduli setting the D terms equal to 0 supersymmetrically. Then a subleading order, you can minimize VF and break supersymmetry. Okay, so let me explain a bit better what these problems are that you encounter when you try to combine moduli stabilization with chirality. So the first one is that there is this tension. And of course, for the visible sector, you have to turn on some flux to generate chirality. And if you want to fix that also via non-perturbative effects, placing an instanton there, generically this will induce chiral intersection, so that the prefactors A will depend on visible sector mode phi. And but then you don't want to break any of the gauge symmetries at the string scale. So this is a phenomenological requirement. The VEV of phi has to be 0, but then AI is 0 also, so you don't get any contribution. So there is a constraint on the flux choice. There is no chirality possible intersection between the non-perturbative effect cycle and the visible sector. There are several ways to overcome these problems, but we tried sort of the most brutal one. Just so in this paper with Kreutzer and Mayhofer, we pointed out that the best place to place these non-perturbative effects is a diagonal del pezzo divisor. So with diagonal, I mean so it is a rigid del pezzo divisor, such that you can always find the basis of fourth cycle, such that it intersects just itself. And in that sense, it diagonalizes the volume form. It's really a local effect. And for that reason, you will never have an intersection, a geometric intersection with the visible sector. It's the visible sector is somewhere else. And of course, you can have an arbitrary number of them. The other problem is with the Friedwitter anomaly. So you have to turn on enough integer flux on any non-spin fourth cycle, D. Non-spin means that the first chain class is odd, to cancel these worldsheet anomalies. So then generically the flux can be written in this way. You expand in a basis of 2 forms with integer coefficient, and then you have this half integer contribution. But then you know that if you want to have an E3 instanton or a Gaussian condensation contributing to the superpotential, generically you need to have a rigid device that is transversal invariant, such that the total flux on it is 0. Otherwise the flux goes to minus itself, and the configuration is not under the orientifold, and the configuration is not invariant. So, but the total flux is this combination, F minus B, which should be 0. But then this Friedwitter anomaly, if the cycle is no spin, is telling you that F has to be different from 0. And so the only way to get a curly F equal to 0 is to choose B. a possibility, so that B cancels F. But of course, you would like to have, say, many cycles getting non-perturbative effects. But once B is fixed to cancel enough integer F on a stack A, generically forces F different from 0 on a second non-spin stack B, unless these two cycles don't intersect. So then the point is that this Friedewitz anomaly generically, exactly because of this caveat, prevents to have more than one non-perturbative effect to fix the Chiral moduli. And even here, there might be other solutions, but we tried the most brutal one again. So just fix the moduli using one non-perturbative effect. And this leads to this large volume scenario that Ki-Woon was also talking about, where the volume is fixed by the interplay of alpha prime corrections, and you need just one non-perturbative effect, again supported by a single diagonal del pezzo, which was the same requirement to avoid the previous problem. The D terms, you know, when you turn on a flux, then you generate a moduli-dependent Fi term. This is the expression. You see that when you turn on this flux. And this is the generic expression for the D-term potential. So if the value of charge field is 0, then the D-term conditions imply just psi equal to 0. But then this might force the shrinking of one or more cycles to 0 size, and this can be problematic. In fact, if you expand this expression for psi, then you see that you get this expression where these are intersection numbers and these are flux quanta. You know, this combination is in practice the U1 charge of the Chiral moduli, which are these T's. So these are the two cycle moduli. So generically, you might say, okay, I get a system of homogeneous linear equations in all my Chiral moduli, H11 of them. But of course, as I said, these non-perturbative cycles do not enter into these equations because there is no flux on them, they are diagonal, they don't intersect. And so in general, the number of unknowns will be H11 minus N and P. But then you will have a matrix of this system with generic rank D, and if D is equal to N, then the only solution is the trivial one, where all the cycles shrink down to 0 size. So the only way to avoid this is to do your model building carefully, ensuring that D is less than N. So you fix only D Chiral moduli with the D terms, the corresponding axioms get eaten up, and the real parts get a mass to the order of the string scale. So you will be left over with N minus D flat directions, not fixed by the D terms, and then you can use this F term potential to fix them. So if this is 1, so the number of directions left, number of flat directions left over by the D terms, then you have just one free parameters, and then all the Chiral moduli Tj are fixed as T star, the same size. And then the requirement to get a visible sector gauge coupling G minus 2, which is T star squared, of the correct order of magnitude, is telling you that this T cannot be extremely large. So you cannot get these large volume scenarios if the D terms just leave one flat directions. So you need that the number of flat directions left over is at least 2, so that one is constrained to be small by the requirement of getting the right value of the visible sector gauge coupling, and the other one can be exponentially large. So what is the minimal requirement? If I set D equal to 1, at least one D term we always have because of the visible sector. Then from this expression, you see that D is 1, N has to be 3. Then I go up here. If I take the minimal case where the number of non-perturbative diagonal del pezzo is 1, H1 has to be 4. So this is the minimal requirement. And then how do we fix the moduli? So W0, we fix it of the order 1, so without any tuning. Then, as I was saying, D combinations are fixed by the leading D term potential. And so D actions get eaten up by anomalous Z1s. And the Chiral moduli, the real part, get a mass to the order of the string scale. Then you have these NP diagonal del pezzos fixed by non-perturbative effects. These are rigid cycles, and they should generate these effects. And they get a mass to the order M3/2, and also the corresponding axioms get a mass of the same order of magnitude. Then what happens to the remaining moduli? That will be generically H11 minus N and P minus D. And as I said, this has to be greater or equal than 2. And these are fixed perturbatively, generically. So the volume mode by alpha prime corrections at leading order, so that the compactification manifold is compact. And then a subleading order, you can fix them via, for example, string loop corrections. So, and the axioms corresponding to these guys will remain, given that they are not fixed non-perturbative, would remain exactly massless. So at least in the simplest scenario, you have at least 2 light axioms. But then when you consider H1 with the order 100, then you expand that this number of axionic fields is very large, and this leads to an axiverse. And these are all massless, so one of them would be the QCD axiom that gets the mass via the standard QCD instanton effects. And then you expect that all the other ones might get amassed by a higher order non-perturbative effect of this form. And Mark will talk about this. Yeah. So far I was discussing just D-branes in the geometric regime. But of course, you would like maybe to have also D-branes as singularities, because here there are quiver theories where people can get a very nice phenomenology. And even in this case, the diagonal del Pezos are crucial to embed the quiver theories, exactly because they intersect nothing else. And so you could either have an instanton there with a flux, total flux that is 0, or you may want to put the visible sector there with the flux at this point that is different from 0. And then once you turn on a flux there, then you generate an Fi term. And then in this combination, because of the triple intersections, then you have that this reduces just to the volume is the Pezzo divisor that shrinks to 0 size because of the D terms. Of course, you need two del Pezzos, two DPN divisors, which are exchanged via the orientifold involution. And so you need at least one orientifold odd modulus. And then you know that these two DPs do not intersect each other, so they do not touch the U7, and you get UN groups, so unitary groups that you like for phenomenology. Of course, on top of that, you still need another diagonal del Pezzo with the standard non-perturbative effects to fix the moduli. Then the stabilization of the bulk moduli is the same as before. And again, the minimal setup involves H11, which is 4, because you have H11 minus, which is 1. This is the G modulus that comes from the reduction of B2 and C4 and C2. And then you have 3 H11 plus T moduli, where 1 is the volume of the local blowup, 1 is the non-perturbative cycle, and 1 is the volume mode. And then, as you know, a DPN divisor has n plus 1, 2 cycles, where 1 is the canonical class. This is always the 2 cycle of the Calabi-Yau, because this dual 4 cycle is the volume of DPN itself. Okay, then there are other 2 cycles. And a DPN has always 2 anomalous U1. So then the number of moduli fixed by the D terms is 2. And these are the G modulus, like this coming from the reduction of B2 over this canonical class, and the local blowup. And the corresponding actions are written up. Then you have these other diagonal del Pezzo and the volume, which are fixed by non-perturbative plus alpha prime effects. And then in the case where H01 is greater than 4, then in general you need also other perturbative effects to fix the moduli. How much time is left? 15 minutes. Okay. So here I had just a few slides with just the details of an explicit example where in the first paper with Valandro and Meyerhofer, where we managed to fix all the moduli and cancelling all the tadpoles for this particular kind of toric ambient variety. But maybe I'll skip the details of this because I want to go straight. I'll just here leave these things for anyone who would like to see them. These are just the details of the construction. Okay, because the other thing I would like to discuss is getting the Sitter vacua from E-1 effects. So in the large volume scenarios, we can get the Sitter vacua either via D-term uplifting, and for example, in the paper which came out today, we have a nice example for models of the quiver locus where the D-terms can give the Sitter vacua, or we have the standard anti-branes with warping. But then in this paper, we pointed out that there might be new sources for uplifting, considering these E-1, D3, fractional D3 branes, and E-1 non-perturbative effects at the singularity. So not just the visible sector, but also the hidden sector supporting the non-perturbative effects can be at the singularity. So then people generically always in the literature studied these kind of gauge instantons for dynamical SUSY breaking and ADS-FT, but always in the non-compact case where the Calabi-Yau is non-compact. So then what we try to do is just, okay, let's consider now the Calabi-Yau that is compact and see what is the effect of this non-perturbative correction of the singularity for the bulk moduli. So we consider the simplest case with 2 moduli, like the volume, the large cycle, and this diagonal del Pezzo. And on top of that, the blob mode of this other singularity where we put these non-perturbative effects, Q. So then you get this singularity for rho equal to 0. Then the Kähler potential as, okay, this part with the dilaton, This is the standard part with the Chiral moduli, the volume, and the alpha prime correction, the leading order alpha prime correction. And then you have this expansion around the singularity for the blow-up mode rho. The superpotential is the part is a 3-level that depends on the dilaton. And then we have the standard non-perturbative correction in the geometric regime for this del pezzo divisor. And then we have this rho that is at the singularity. And there the gauge kinetic function is given by the dilaton plus a shift that is in practice the U1 charge of this Q modulus. So then you can study the D terms again, and you can show that they are the leading order effect, and they fix the blow-up Q at 0 size, so at rho equal to 0. And then you look at the F term potential for Q, and you see that this gives an uplifting term. Because so the F term potential, you get something like this, where so the first two effects, e to the minus 2a tau s, e to the minus a tau s, they get from this non-perturbative effect in the geometric regime. This term that is proportional to this zeta is the leading order alpha prime correction. And then you get this new effect that comes from this other non-perturbative correction at the singularity. Actually, what you get, because you see that for this non-perturbative correction, once you use the standard F term supergravity expression, you get two contributions. One is positive, one is always negative. The minus sign comes from the axiom minimization. Also, for this guy, you would get two contributions. One positive, that is this one, that goes like e to minus 2 over tau big 3/2, like this one. And you will have another one with a minus sign that goes like e to the minus 1 times b over tau big cubed. But actually, we'll have a prefactor that depends on rho. And then once you substitute the VEV that you get a leading order from the D terms, this rho equal to 0, the negative term would vanish. So then you would be left over just with a positive term that can give you the uplifting. And then you see that the potential is the standard LVS potential, like these three terms, plus this V up. And then V up has this form that is very similar to what you get when you have anti-branes and warping. Because you see, you have an inverse factor of the volume, and then you have something like the warp factor here, because the warp factor is an exponential of a ratio of fluxes, and even here, the exponential of the VEV of the dilaton, and the dilaton is also fixed as a ratio of fluxes. So you can do the same tuning that you do with anti-branes. But actually, here the tuning is also a bit alleviated dynamically, since when you work out the minimum, you have the tau s goes like gs to the minus 1, and the volume is the exponential of tau s. But then you also know that the VEV of s is giving you g string to the minus 1. And so the VEV of s is dynamically more or less as tau s. So these, and then if you can choose a equal to b, so then this thing goes like e to the minus 2a times tau s over the volume, which is the same scaling of the large volume scenario potential. So then naturally you have the v up scales as v LVS that goes like volume to minus 3. And on top of that, the effective action is manifestly supersymmetric. Okay, finally, we'd like to discuss some applications to cosmology. Then you know that cosmology, when you consider single fields low roll inflation, you have these two parameters, epsilon and eta. They have to be both much less than 1 to get inflation. And the second condition, once you use the Friedmann equations during inflation, is telling you that the mass of the inflaton phi has to be much less than h during inflation. But then once you use the F term supergravity scalar potential, which is this one, then you have that even if the standard dimension for scalar potential is flat, and then using this potential you can satisfy these equations. Here you always generate dimension 6 Planck suppressed operators, which have this form, from expanding this factor e to the k. And these corrections bring you the mass of the inflaton of the order h again. So to solve this eta problem, then you need to have two conditions. One is a flat inflationary potential, and then a mechanism to suppress the corrections for these higher dimensional operators. And the Chiral moduli are promising inflaton candidates, and I'll be focusing on the real part of them. And these are volumes of 4 cycles, which might have different topologies, like blow-up modes, vibration moduli, or the overall volume mode. People also focus on the imaginary part, which are axions, which give also nice inflaton candidates. But here, when you focus on the real part, you have also a natural solution of the eta problem, because when you look at the no-scale structure of the type 2b Chiral potential, you get that this is the Chiral potential, and the leading order, the potential is 0. So then you have to look at the first correction that breaks this no scale, and it turns out that this is the leading order alpha prime corrections. Sorry, this was the parameter we was calling zeta before, now it's psi. So you see, you expand this, but this depends just on the overall volume mode. So it means that the leading order in this moduli space, you're lifting just one direction, which corresponds to the volume mode. So then all the other directions, like H01 plus minus 1, are still flat at leading order. And they are natural inflaton candidates. Or in other words, the inflaton has to be a combination of moduli orthogonal to the volume. And these of them will be naturally light. The other thing is that the three-level Chiral potential depends also only on the volume mode, which means that if I expand e to the k and the volume is not the inflaton, I would not generate these dimension 6 Planck suppressed operators. Actually, once I include corrections to the three-level Chiral potential that introduce a dependence on all the moduli, then I will get these dimension 6 Planck suppressed operators, but with this coefficient c that was in front of them, that is not order 1, but it would be volume suppressed. That's the way you can solve this problem. Of course, the first question you should ask is that are there other perturbative corrections which break the no scale? The answer is yes. There are also string loop corrections which might introduce a dependence on all the moduli. So you will have not just alpha prime, but also string loop corrections. And if these corrections beat the alpha prime and introduce a dependence on all the moduli, then this argument doesn't work. But then it turns out that they are subleading with respect to the alpha prime corrections at the level of the scalar potential because of an extended no scale structure, a cancellation of leading order of these corrections. And then, so the leading order, as I was saying, you develop a potential for the volume, and that sets your Hubble constant during inflation. All the other directions are flatter, and then you should somehow lift them a bit to generate the inflationary potential. And there are two effects, as I was saying. One is these perturbative G-string corrections. The other is non-perturbative, the standard non-perturbative corrections, which are tiny because of the exponential suppression. And then the inflaton, as I was saying, should not be the overall volume mode. Or in other words, you should do inflation keeping the volume stable. And two examples are like blow-up moduli or vibration moduli. And then you can start combining 1 and 2 with A and B, and we found different models. Of course, here I'm making it very simple, but you have to work a lot to get that. But it's just the main idea why this works. And you get different models with different prediction for the cosmological observables. But the main thing I would like to say is that these were all single field inflationary models. And this is what people focused on mainly. And the reason is, I think, it's fair to say, is for simplicity. Because it's already complicated to solve the zeta problem, so it doesn't make sense to consider multi-field inflationary dynamics if you cannot solve the single field inflationary dynamics. Then people, okay, there are some now solutions which are based on symmetries, like for the axions or this no-scale, extending no-scale structure. And one can work out the prediction for the cosmological observables, like the spectral index, the tensor to scalar ratio, the amount of non-Gaussianities, and so on. And generically, the tensor modes tend to be negligible, but there are a few models where you can get largish R for Transplanckian field range. And but this is not very common, also because of the talk that Joe gave last week with these entropy bounds. And the other thing is that non-Gaussianities are negligible due to the very weak inflaton self-interaction. This is just a single field whose potential is mimicking a cosmological constant, so it's just flat. So the 3-point function, the self-interaction is almost negligible. But then the question we should ask is this a generic case from string theory? Because if Planck observes non-Gaussianity, then we should ask this. And I think the answer should be no, because a generic compactification has many moduli. So once we find the mechanism to render one of them lighter than H, then generically when you have many of them, not just one will be lighter than H, but the same mechanism will bring you more moduli lighter than H. So then some will be heavier and some will be lighter than H during inflation. So then the heavy field will sit at the local minima, where the light fields get large quantum fluctuations. One will be the inflaton, and the other ones will get large quantum fluctuations, which can provide no standard generations of the CMB density perturbations, and then generically large non-Gaussianities. So exactly to stress this point, recently in two papers we work out two mechanisms where you generate, when you have a multi-field inflationary dynamics, and you generate large non-Gaussianities, so the order FNL, or the order 10 observable by Planck in these papers, in these two papers. So just very quickly, so the first one is a modulation mechanism in the sense that you have two fields like the H, phi and psi. Phi is the infraton, and psi is the modulating field. So that the coupling of phi, the infraton, to the visible sector degrees of freedom depends on psi. So then you have a non-standard generation of density perturbation by the fluctuation of this modulating field phi, that is very light during inflation. So that reheating takes place at the same time in different regions of the universe. So that means that I'm neglecting the standard mechanism due to the infraton fluctuations. And of course, actually, we checked in the model that this is the case, but with different efficiency because of this fluctuation in the coupling. And this different efficiency gives rise to density perturbations. But then now also to large non-Gaussianities because these density perturbations are not generated by the infraton. And we combined, for example, this phi, the infraton in this case was a fiber modulus with a loop generated potential, and psi, the modulating field, was a blow-up mode with these Pauli-Instanton corrections. And then we work out another model, a curvaton mechanism, where phi is the infraton and psi is the curvaton field. So they both have a mass less than h, but the mass of phi is greater than the mass of psi. So this is phi is dominating the energy density of the universe, so that is the infraton. And this decays phi before psi because of this mass relation, giving rise to reheating. But then nothing happens here, or if you want, you will have generation of density perturbation by the infraton fluctuations, but this is something that we check to be negligible, because then you have no standard generation of density perturbations by the fluctuation of this curvaton field, and then they get generated when psi decays out of thermal equilibrium, when his isocurvature fluctuations get transformed into the standard density perturbations, and we get also here large non-Gaussianities. And we have a strict embedding of this, where phi, for example, is a blob mode with these instanton corrections, and the curvaton is a fiber modulus with loops. Let me go to conclusions. So we are presenting concrete chiral models with Chiral moduli stabilized, presenting a general strategy to combine Chiral moduli stabilization with chiral D7 brane or fractional D3 brane models in type 2b flux compactifications. The geometric data are described by toric geometry, which allows to make specific choices of brane setup at fluxes that give rise to GATT or MSSM-like models. So I didn't have time to discuss these details, but you can find them in the papers. And this is the same thing for the consistency constraints. And also in the paper, we have compute the scalar potential, minimize it, obtaining different interesting scenario. Realizing for the first time the large volume scenario in a concrete model, not just in the sort of just looking at the effective supergravity theory. And this moduli stabilization gives rise to an axiverse, where we can get also this de Sitter vacuum from these D3 minus 1 instantons. And the Chiral moduli are also promising infraton candidates, because there is a solution to the data problem based on the no scale plus the extended no scale structure. And the general situation, I would claim, that is a multi-field inflation dynamics with FNL of the order of 10 detectable by Planck. Finally, the last slide is the outlook. Of course, as I was saying, we didn't turn on three-form fluxes, and it's something that we would like to do that explicitly to fix the compact structure moduli, the dilaton, and also the D7 deformation moduli. And the other thing is that we have not been, this was the first step to combine this D-brane model building with moduli stabilization. So we had just a chiral toy model. So the first step, we would like to refine the construction of the visible sector. The other thing is we have a long list of Calabi-Out reforms with this program part, worked out by Kreutzer and Skarke and Brown and Walliser. And we would like to try to automatize the search for a consistent and phenomenological viable model. Because what we did here, we thought what was the general way to fix the moduli to avoid all these problems. And then we picked just one model. That was a K3 fibration, because we liked that for phenomenological reasons. But now we would try to, for example, to get a better chiral spectrum Yukawas to automatize this search. The other thing is that in the paper on the global embedding of branes and singularities, we had just fractional D3 branes without any kind of flavor D7 branes, just for simplicity. And this is something that we would like also to understand and add, maybe following this interesting paper, which came out also recently. The other thing is to derive the details of SUSY breaking, especially understanding if we have sequestering or not in these models. And also this the Sitter vacua, using these non-perturbative effects, we would like to have an explicit realization of this. The same is true for cosmology. even here we would like to have a model with a compact Calabi-Yau moduli stabilization where we can really derive all the details of these promising inflationary scenarios. And finally, another thing that they didn't talk about is that in all these models, even though we didn't look for them, just by a tadpole cancellation, we were forced of having always branes wrapping large cycles. And in that case, you always have a hyper-weak interaction there with these hidden photons that have which are very light because the volume is huge, and they have a kinetic mixing with the ordinary photon, and they might have a very nice and interesting phenomenology. And finally, applications to F theory. Okay, thank you.
So you mentioned that you realized the large volume scenario in a complete Calabi-Yau compactification. So did you also check the complex structure moduli?
Yeah, this was my claim that we did not.
You did not.
Yes.
Okay. There's another consistency condition. There's another Fried-Witt anomaly.
Yeah, that is a good question. Yes. Yeah. So so the other, but I think that condition applies not just to large volume. It's just a condition that applies in general to modular stabilization. So the other one is that the other source is when you turn on H3, so the pullback of H3 on any wrap full cycle should be 0. And so we checked this. So in the last paper where we had the global embedding, we checked that all the wrap full cycles have the third Betti number, which is 0. So all the 3 cycles are trivial, and then you know that you don't have this problem. But in the first paper, so we cancelled always the D7 tadpole, adding a Whitney brane. So this kind of, we tried to cancel that. So what we did is that we built our setup with D7 branes according to some sort of model building requirements. And then, okay, we had some D7 tadpole that we cancelled. And then we said, okay, let's try to cancel it with just one D7 brane. So we had this Whitney brane with a double intersection with U7. And there in general is not true that all the 3 cycles are trivial. But I was saying that this thing is more generic because then you know that every time you wrap a 4 cycle which has non-trivial 3 cycles within the Calabi-Yau, then because of this Fried-Witt anomaly, you should not be allowed to turn on a flux. And then how do you fix the complex structure modulus? I think it is an open problem. Of course, if you ensure that all the 3 cycles are trivial, then.
I have a question on this uplift by the lower D instanton. Is this, did I get it right? Is this a D3, D-1 bound state instanton, or what exactly? Or is it
this is like, so we took these papers where people studied dynamical Susy breaking, where they had these quiver theories with fractional D3 branes, and then they put an E-1 instanton there to realize gauge instantons at the singularity. So this is the construction we have in mind.
So it's a gauge instanton.
It's a gauge instanton, realized as this E-1 instanton. It's like when you have a D7 with an E3, something similar.
And you have the D3 brane as well. You have the space filling D3 brane and the D-1
Yeah.
coupling to that.
Because then I'm not sure if you're just an E-1 if that contributes or not.
Exactly. That was
Because then you would get, where is this? Yeah. So in that case, I think you would get this H is 0. So you would get like e to the minus s. And I'm not sure if that contributes.
But then B is an operator. If it's a gauge instanton, B is not a constant.
That is true. Then, just for simplicity, I didn't discuss this here. And then in the paper with, so there is a tension here actually, because so in the simplest case, you might have, okay, this will be, because this is charged, and then this depends on your fields there. So you need your fields to get a VAB. But then you should be careful that, you know, when you look at the term potential, when they get a VAB, they might resolve the singularity. So it's not true anymore that you are there. But then the thing is that given that this is a hidden sector, you're not forced to have that these VAB are 0. So you might even have more than one field charged, so that they cancel off one against the other, and then you generate that. Or
Runaway?
then you need to add other effects to stabilize that. Or there is another possibility that the singularity is resolved not just with one blow up, but you have more than one blow up, and then the situation is more complicated. And you can
One small question. What's your dark matter candidate? Is it the axion? Is it a regular LSP, or is it hidden sector?
Yeah, so this is so Mark now will discuss this. So it depends, because so according to these large volume scenarios, because this is a scenario, and then you can have different models there, where you can have the visible sector in this geometric regime or at the singularity, and then things change. For example, what I was talking about here, where the visible sector is in the geometric regime, then you get that one of these local axions has to be left over because of this argument with the d terms. And then you will have a decay constant which is given by the string scale. And in order to get TV scale SUSY, the string scale is intermediate. So you are exactly in the allowed window. But then you have also some moduli which are like the overall volume mode, which is light. And so you have a problem with this cosmological moduli problem. And so you will need some mechanism like thermal inflation or the decay of M moduli that would dilute this, the light modulus, but then they would dilute also the axions. And given that they are in the intermediate window, then I would assume that once you dilute them, they don't contribute to dark matter that much.
So let's thank Michele again.